is Riley Short. I'll be giving my presentation on the use of graphene as a medical-grade silicone rubber additive for application as a strengthening agent and microbial inhibitor of Escherichia coli and Pseudomonas aeruginosa. Urinary catheters are probably one of the most commonly used pieces of medical equipment today, but just because they're so commonly used doesn't mean they're perfect. Urinary catheters account for almost 75 to 80% of all urinary tract infections, and this is because the urinary catheter acts as a substrate for persistent biofilm-forming bacteria such as Escherichia coli and Pseudomonas aeruginosa to form upon it and further cause an infection, which is very hard to get rid of, and it costs a lot of money from the patient and the hospital to get rid of it as well. Not only are catheters flawed aseptically, but they're also flawed structurally. Most catheters are made of a weak silicone rubber, and because it is weak, it can sometimes buckle within an insertion, which causes a lot of pain to the patient. And then also, to offer any structural strength, you have to have very thick walls to the catheter, which furthers discomfort to the patient. So if you could add something to a silicone that's used in a urinary catheter to lower the amount of biofilm growth and also increase the structural strength, then you can have a better product for patient use. I worked with a substance last year called graphene, and as you can see here, it is a 2D hexagonal carbon structure which is extremely lightweight and extremely strong, and has been used in many applications such as solar cells, water filtration, and more. But recently, it has been found that graphene has had antibacterial properties towards Escherichia coli. So if graphene was used in a silicone rubber, it could potentially lower the amount of biofilm growth from Escherichia coli and hopefully Pseudomonas aeruginosa, while also increasing its structural strength. So the purpose of this study was to explore exactly that, to see if the addition of graphene within a silicone rubber would not only decrease the amount of biofilm forming colonies of E. coli and Pseudomonas, but also to increase the structural strength of the silicone rubber as well. So of course I hypothesized that if silicone had graphene added into it, then it would not only lower the amount of Pseudomonas aeruginosa and Escherichia coli biofilm forming colonies grown upon it, but it would also increase the amount of load that a sample could handle as well. So my independent variable being either the presence or absence of graphene within a silicone rubber, and my dependent variables being the number of Escherichia coli K12 and Pseudomonas aeruginosa PA01 forming colonies upon my sample disc that we'll see in a second, and also the amount of force that each of my sample discs can handle as well. So my experimental groups being either a pure medical grade silicone sample or a silicone graphene composite sample disc, and then also a control group of a polycarbonate disc. And this polycarbonate disc was used just to get baseline data of the biofilm. It is excellent at allowing biofilm growth upon it, but it would be a poor substitute for a catheter material because it is very rigid and you want a catheter to be flexible. So good baseline data, poor substitute for a catheter material. And then some of my control variables just being the mass and shape of each of the silicone graphene and silicone composite discs used, the temperature and time they were allowed to cure, the strains and exposure time to each of the bacteria, and also the load limit and displacement limits for my compression testings. So to create the disc that you can see here, I traveled to Missouri University of Science and Technology, where Dr. Jehangir Masood graciously allowed me to operate his equipment in order to create my discs. To create my disc, you can see the silicone in the top right, the silicone graphene in the bottom right, and in the middle you can see my polycarbonate. This polycarbonate was pre-made, of course. But to create the silicone and silicone graphene, I combined 10 parts of a base elastomer silicone with 1 part of a curing agent, allow this mixture to ball mill for 30 minutes, pour it into a cylindrical mold that you can see on the far left, and allow this mixture to cure for 15 minutes at 100 degrees Celsius. Once this was cured, the cylindrical piece that it had formed was removed and then sliced into 5mm thick discs. For the silicone graphene, a similar procedure is followed with 10 parts of a base elastomer and 1 part of a curing agent. Then I also added 1% of the total mass of the mixture in graphene. Then this process was still 30 minutes of ball milling and also 15 minutes of curing at 100 degrees Celsius, then removed and sliced into 5mm thick discs. For my biofilm testing, I traveled to another lab at Missouri University of Science and Technology, where I had contacted Dr. Dave Westenberg to allow me to use his biofilm reactors. One of them you can see in this far left picture. These biofilm reactors were both filled with 300 milliliters of 1% tryptic soy broth, and one was inoculated with an Escherichia coli's K12 strain, and the other with the Pseudomonas aeruginosa PA01 strain. Once they were inoculated, my sample discs were all sterilized using a UV straddling to ensure that no bacteria was left upon them. And then 6 sample discs from each of my test groups were placed into each of the biofilm reactors, where they were allowed to collect biofilm upon them for 72 hours. After this period was up, the discs were sent through a washing process, which you can see in the middle picture, to rinse all the planktonic cells that did not form biofilm off of them. Once these were rinsed off, then the biofilm cells were scraped off into separate saline solutions per each disc, and then the saline solution was plated upon to tryptic soy agar plates. And after they were been plated, they were allowed to colonize for 24 hours, and then the number of Escherichia coli and Pseudomonas aeruginosa cells were quantified. To quantify the Escherichia coli biofilm forming cells, I use a random sampling method, which you can see in the right picture, where I selected 20 random squares off of a grid and quantified the number of colonies in each of these squares. And for the Pseudomonas aeruginosa, unfortunately, it had grown to an unquantifiable amount. So instead, I quantified a foreign organism that had found its way into the plates, because it still shows that biofilm is excellent at allowing bacteria to adhere to it. So instead, I quantified the foreign organism that had found its way in. So for my compression testing, I traveled to another university, Missouri University of Science and Technology lab, where Mr. Ryan Grossmere allowed me to operate a tensile testing unit, which you can see in the right picture. This tensile testing unit was equipped with a 2,000 Newton load cell, which you can see in the far left. And this 2,000 Newton load cell was calibrated to the top of each of my discs. And when it was calibrated, it would be displaced downward 4.5 millimeters, so the disc would be compressed to a 0.5 millimeter thickness. And until it was either displaced 4.5 millimeters downward or reached a load limit of 1,800 newtons to ensure the safety of the load cell, it would record data over time of the displacement value and also the force exerted upon each disc. And for all my data analysis, all my data was recorded in Microsoft Excel spreadsheets, where it could be interpreted, it could be subjected to statistical analysis, like my ANOVA single factors that I had used for all of my experimentation, where I had an alpha value of 0.05, and I was looking for a p-value of less than 0.05 to determine significance, and then also used to create graphical representations of my data. So for my biofilm experimentations, you can begin to notice that for both the Escherichia coli and foreign bacterial colonies, the polycarbonate actually had lower numbers of bacterial forming colonies than both of my test groups. Now, like I said in the beginning, polycarbonate is excellent at forming biofilms upon it, but I believe it had less in this scenario because of the amount of surface area for each of the test groups. My polycarbonate discs were pre-cut as a factory setting, so you have a very smooth surface, whereas I manually had to cut my silicone and silicone graphene discs. And also during the curing process, bubbles had formed, so obviously there is more surface area upon those, offering for more room for the bacteria to grow upon. But for the silicone and silicone graphene, these do have almost identical amount of surface area. And when you compare the silicone and silicone graphene, my silicone graphene significantly has lower numbers of Escherichia coli and foreign bacterial colonies when compared to my silicone groups. For my compression testings, you can begin to notice between my silicone and silicone graphene that my silicone displacement rates increased at different rates. They had different slopes. Now this isn't because the discs were any different or they performed any differently. This is because that the load cell was displaced at different rates just to speed along the process as I was running out of time on that day. So this doesn't change the results, but what you really want to look at is the ending point of each of these lines. The final ending load value, the final load that a disc can handle. So for that, I went ahead and averaged these for my 2 test groups, and you can see that my silicone graphene had a higher ending load value on average than my silicone disc, proving it has a higher structural strength in it. And after running this through an ANOVA single factor, it was again proven significant, like by biofilm testing. So to conclude, if you would use a silicone graphene catheter within a hospital for a patient, it would be less likely to contract a urinary tract infection from the patient because it would have less biofilm growth upon it than a pure silicone catheter. And then because it is structurally stronger, you could reduce the wall size of the catheter, lowering the amount of discomfort to the patient, and also decrease the likelihood of a buckling motion, which also is very painful to the patient. So this could save hospitals so much time, money, and effort to cure urinary tract infections because they will be less likely, and also the patients will have less discomfort and they will be happier with their product. So some future studies I would just really like to look at, I would like to see at varying amounts of graphene, would also have varying effects on the biofilm growth so I wanted this product to be as cost effective as possible. A silicone graphene catheter would not be that much more expensive than a pure silicone catheter. It would be approximately like $15 to $20 more than a pure silicone. But would you rather pay $15 to $20 more for a silicone graphene catheter at the moment, or would you rather use a pure silicone catheter and possibly have to pay hundreds of dollars for antibiotics to get rid of a urinary tract infection? So I'd also like to see if graphene has antibacterial properties with gram-positive and gram-negative bacteria, just because both of the bacteria in this situation were gram-negative, so I want to see if it has similar or different effects with gram-positive bacteria. And I would also like to look at a new design of a catheter put out by Duke University. As you can see with this design, it has a lower cavity and a main cavity. And this lower cavity is flooded with water, and by doing that, it moves the lower lip of the main cavity up and down. It physically breaks up biofilm within it. But something you can notice, this product doesn't look very feasible because it is very thick at the moment. But with a structurally stronger silicone graphene, you can reduce the wall size down and make this a feasible product. And I am currently in contact with Mr. Brad Levering, who was part of the research group that designed this, to see if we can get a collaboration on how to make a feasible product. I would just like to acknowledge all the 3 professors I was able to work with after I contacted them, and they allowed me to use their lab, and also my research advisors at Camden High School that answered any questions I had and reviewed my paper. Here are just some of my references, and at this point I'll be taking any questions. Thank you.
So, Riley, what sparked your curiosity into this, or how did you come up with such a detailed project?
Okay, so last year I did work with graphene. It was in a completely different scenario. I used it in a catalytic converter within an automobile exhaust system. And it's such a unique product. It's being used in so many parts of industry. And I do have interest in the medical field. I plan on being a surgeon when I get out of college and out of medical school. So I really wanted to do something medical related. So I found out that graphene had antibacterial properties, so I started looking at ways where I could use it in a medical setting, and I found other articles on how urinary tract infections are so predominant from catheters, so I thought about putting 2 and 2 together and it worked well.
Okay. So, and on your number of E. coli colonies, you didn't graft out the Pseudomonas because of the contaminant, is that correct? Did I understand that correctly?
I didn't graft the Pseudomonas aeruginosa because it had grown to an unquantifiable amount.
Okay.
So I did a serial dilution for my sampling. So the E. coli was serially diluted from a 1 to 100 ratio. And originally I had done that with the Pseudomonas as well, and it grew to an unquantifiable amount. So I went back and serially diluted it to a 1 to 10,000 amount, and it still grew to an unquantifiable amount. So Dr. Westenberg at S&T advised me to just count the number of foreign bacterial colonies because it still gives a representation of the amount of biofilm that would have grown anyway.
So by foreign bacterial colonies, are you talking like a contaminant?
Yes.
Pseudomonas? Did you ever type that out to see what?
No, I did not type that out. I asked Dr. Westenberg if I needed to, and he said it wasn't necessary because with a urinary tract infection, you can have so many different types of bacteria adhering to it, so he didn't think I needed it.
I was just wondering, because your numbers on E. coli only vary about around 500 between the silicone and the silicone graphene, if I'm not following your track, right? So still, I think that might be a significance to urinary tract infection. Does this come as a medically treated or pre-treated substance to retard this? Is there a way to do that possibly for future studies? Maybe?
So if graphene is basically, if it's able to be used in the medical field as of now, if it's
right, because you only have like a difference of 1,000 colonies right now from your graph, and so I don't see, that doesn't look to me like that big of a significance, that it's retarding your bacterial growth that much.
Well, after serially diluting it, it originally did have a lot of growth, and from my perspective alone, I did think it would have a